Hello, and welcome to Sparx Science for Sleep, where the mysteries of the universe wrap around you like a soft blanket. I'm so glad you're here, perhaps curled up in bed, your head resting on a pillow, ready to drift into a peaceful adventure. Take a slow, deep breath. Let your body melt into the softness of your bed and feel the worries of the day fade, like distant constellations dissolving into the night. Tonight, we'll wander to the edges of the universe, where science weaves tales of wonder, each one a thread in the great tapestry of existence. Imagine yourself floating in a tranquil void, surrounded by a shimmering veil of starlight, each glow a whisper from a time long past. If you're listening from a cozy corner of the world, maybe with a window open to the night sky, I'd love to hear about it. Drop a comment to share where you are, what time it is, and what the stars look like where you rest. This journey is for you, whether you're here to relax, to dream, or to let the universe's secrets cradle you to sleep. Let's begin by drifting toward the light that shapes our view of the cosmos. Breathe deeply now, letting your mind soften, as if you're gliding on a gentle cosmic current, weightless among the stars. The universe we see is painted by light, each photon a traveler carrying stories from the farthest reaches of time. This is the observable universe, a vast sphere stretching 46 billion light-years across. Not because that's the size of everything, but because that's as far as light has traveled to reach us. The universe is 13.8 billion years old, yet its expansion stretches space itself, like a melody growing longer with each note. When we gaze at a distant galaxy, we're seeing it as it was billions of years ago, its light a message sent when the cosmos was young. Picture yourself holding that light, a glowing ember from a fire that burned long before Earth was born. Scientists use telescopes like the Hubble to catch these ancient rays, piecing together the universe's story. As you float here, let the vastness of this idea wrap around you, soothing and calm, like a breeze carrying you toward dreams. Now, let your breath slow, your body sinking deeper into peace, as if cradled by the gentle rhythm of the cosmos. The edge of this observable universe, that 4-6 billion light-year horizon, isn't a wall or a barrier, but a line drawn by time itself. We call it the cosmic horizon, where light's journey to us ends, not because space stops, but because time hasn't given it long enough to travel further. Imagine standing on a quiet shore, watching waves roll in from a distant sea, each one carrying tales of far-off lands. Beyond those waves, more ocean stretches, unseen but real. The cosmic microwave background, a faint glow from 380,000 years after the universe's birth, marks this horizon's oldest light. Discovered by accident in the 1962nd, it's like a whisper from the cosmos's infancy, when atoms first formed, freeing light to roam. As you rest, picture this glow as a warm blanket of light, wrapping you in the universe's earliest memories, inviting you to drift closer to sleep. Take one more deep breath, letting any tension slip away, like stardust scattering into the void. Beyond this cosmic horizon lies a mystery, what exists where light hasn't reached. The universe may stretch on, filled with more galaxies, stars, perhaps even worlds we'll never see, their light still racing toward us across unimaginable distances. This boundary, shaped by the speed of light and the universe's expansion, reminds us that we're part of something vast, yet only see a sliver of its grandeur. Scientists ponder this unseen realm, wondering if it mirrors our own or holds secrets we can't imagine. As you float in this quiet moment, let the thought of those distant, unseen stars soothe you, like a lullaby from the cosmos. We've touched the edge of light's reach, but more wonders await. Let's drift now to a new question. Does the universe stretch on forever, or does it curve back on itself, like a cosmic embrace? Rest here, and let your mind wander toward that next mystery, waiting just beyond the stars. Let's drift now from the shimmering edge of light's reach, where the cosmic horizon whispers its ancient tales, into a deeper question that hums softly in the quiet of the night. Picture a vast, endless meadow under a starlit sky, each blade of grass a galaxy, stretching as far as your mind can wander. The universe, as we left it, is bound by the light that reaches us, but what lies beyond that delicate veil? Is it an endless expanse, or does it fold back upon itself like a gentle loop in a cosmic ribbon? Take a slow, deep breath, and let your thoughts soften, easing into this new mystery. We're about to explore whether the universe is infinite, stretching forever into the unknown, or finite, curling into a shape we can scarcely imagine. This is a question that has puzzled scientists and dreamers alike. A puzzle that feels like a lullaby, inviting you to wonder without urgency, to rest in the vastness of possibility. Imagine a ship sailing across an endless ocean, no land in sight, no horizon that marks an end. This is one way to picture an infinite universe, a cosmos that stretches on without boundary or limit. Scientists have studied the shape of space using tools like the Planck satellite, which map the faint glow of the universe's earliest light. Their measurements suggest that space is nearly flat, like a vast sheet of paper extending in every direction. A flat universe could go on forever, filled with countless galaxies, stars, and perhaps worlds we'll never know. Each galaxy is a cluster of light, like a village glowing in the distance, part of an unending cosmic landscape. The idea of infinity is dizzying, yet soothing in its simplicity. There's no edge to find, no wall to touch, just more space, more stars, more stories. Scientists call this a flat geometry, where parallel lines never meet, and the universe expands without ever folding back. As you let this idea settle, feel the calm of a universe without end, a quiet expanse that cradles you in its boundlessness. Now, shift your gaze to a different scene, as if you're walking across the surface of a vast glowing sphere, your steps light and unhurried. What if the universe is finite, but without edges, like the Earth itself? The Earth's surface is finite. You can measure its area, but you'll never find a cliff where it ends. Walk in any direction, and you'll circle back to where you started, a journey with no boundary. Scientists propose that the universe might work this way too, curving in a higher dimension we can't see, forming a shape called a three-sphere. In this model, if you traveled far enough, faster than the universe expands, you might return to your starting point, passing the same galaxies again, like revisiting a familiar dream. This curvature would mean the universe has a definite size, yet no edge, a cosmic loop that feels both intimate and grand. Researchers look for clues in the cosmic microwave background, searching for patterns that might hint at this looping geometry, like echoes of light repeating across the sky. The thought of a finite universe, curling gently around itself, is like a soft melody, guiding you toward a peaceful rest. Consider now a third possibility, as if you're gazing into a vast, mirrored hall, where reflections stretch endlessly in every direction. Some scientists wonder if the universe could be finite but tiled, like a cosmic mosaic, where space repeats itself in a pattern we can't detect. This is called a toroidal universe, shaped like a donut or a cube with opposite sides connected. If you flew straight through such a universe, you'd emerge on the opposite side, as if stepping through a hidden doorway. The Wilkinson Microwave Anisotropy Probe, or WMAP, searched for signs of this repetition in the universe's oldest light, looking for matching patterns that might suggest space loops back on itself. So far, no clear evidence has emerged, but the idea lingers, like a quiet hum in the background of the cosmos. A universe like this would be finite, yet feel infinite, each loop a new verse in an endless song. The thought of space folding in such a way is a gentle invitation to dream, to imagine a cosmos that plays with its own boundaries, wrapping you in its mystery. Let's pause for a moment, as if you're resting on a soft cloud, drifting through this cosmic tapestry. Whether infinite or finite, the universe challenges our imagination, asking us to picture what lies beyond our grasp. Scientists use geometry to explore these possibilities, drawing triangles across the cosmos to test its shape. In a flat universe, the angles of a triangle add up to exactly 180 degrees, like on a piece of paper. In a curved universe, they might add up to more or less, hinting at a sphere or a saddle-like shape. The Planck mission found that our universe is remarkably flat, suggesting it could stretch on forever, but it might also be so large that any curvature is too subtle to detect. Imagine drawing a triangle on a beach so vast you can't see its curve, yet the curve might still be there, hidden in the vastness. This blend of science and wonder feels like a gentle wave, rocking you softly as you listen, inviting you to relax into the unknown. Now, picture a quiet moment, as if you're lying beneath a canopy of stars, each one a question mark in the night. The idea of an infinite universe brings with it a strange possibility. If space goes on forever, every possible arrangement of matter might happen somewhere, sometime. This is called the cosmic doppelganger hypothesis, where, in an infinite cosmos, there could be another you, another Earth, living out a slightly different story. The math of infinity suggests that with enough space, every combination of atoms repeats, like a melody played on an endless piano. Scientists don't know if this is true. It's a thought born of probability, not observation, but it's a reminder of how vast the universe might be. The idea is like a soft whisper, comforting in its strangeness, suggesting that somewhere, in the infinite expanse, there's a place for every possibility. As you linger here, let this thought drift through your mind, a quiet note in the cosmic symphony, easing you toward rest. Shift your thoughts now, as if you're gliding through a gallery of cosmic art, each piece a different vision of the universe's shape. A finite universe, looping back on itself, offers a different kind of beauty. It's like a book with a definite number of pages, yet no final chapter, because the story circles back to the beginning. Scientists explore this through topology, the study of shapes that bend and twist without edges. A toroidal universe, for example, might connect distant points, so a starship traveling far enough would see familiar stars reappear, like a memory resurfacing in a dream. Researchers have looked for these connections in the cosmic microwave background, hoping to find identical circles of light that suggest space repeats. So far, the universe seems too vast for such patterns to be clear, but the search continues, like a quiet quest for hidden doors in the cosmos. This idea of a looping universe feels like a gentle embrace, a reminder that even in a finite cosmos, there's room for endless wonder. Let's drift a little further, as if you're floating on a soft breeze through this cosmic landscape. The question of whether the universe is infinite or finite isn't just about size, it's about meaning. An infinite universe suggests a cosmos, where everything happens somewhere, a place of limitless possibility. A finite universe, curving back on itself, feels like a home, a place where every journey might lead back to the start. Scientists use tools like the cosmic microwave background to probe these ideas, measuring its patterns to understand the universe's geometry. The flatness they've found leans toward infinity, but it's not a final answer, just a clue in a much larger puzzle. Imagine the universe as a vast library, its shelves filled with stories that might go on forever, or circle back in a single, elegant volume. This thought is like a soft light, glowing gently in your mind, inviting you to rest in its mystery. As we linger in this quiet moment, the universe's shape remains a question without a definite answer, a melody that plays on without a final note. Scientists keep searching, using mathematics and telescopes to chase the truth, but for now, the cosmos keeps its secrets, like a dream half remembered. Whether infinite or finite, the universe is a place of wonder, a vast canvas painted with galaxies and possibilities. Now, let's let our minds wander to a new corner of this cosmic story, where the universe might not be alone, where other universes, like bubbles in a cosmic sea, could shimmer just beyond our reach. Take a slow breath, and let this question carry you gently forward into the next chapter of our journey, where the idea of a multiverse waits to unfold. From the gentle question of whether our universe stretches endlessly or curls into a cosmic loop, let's now glide into a stranger, more wondrous realm, where our universe might be just one note in a grand symphony of many. Take a slow, deep breath, and imagine yourself as a tiny spark of light, floating in a vast, shimmering sea of bubbles, each one glowing with its own stars and stories. This is the idea of the multiverse, a tapestry of countless universes, each born in a moment of cosmic magic. We're about to explore the theory of eternal inflation, where bubbles of universes form in an ever-expanding ocean of space, each with its own rules, its own dreams. Let this thought settle softly, like a feather drifting down, as we wander into the mystery of what might exist beyond our own cosmic bubble, a place where the very laws of nature could dance to a different tune. Picture a vast, frothy ocean, not of water, but of raw energy, bubbling and churning in the earliest moments of existence. This is the scene set by cosmic inflation, a theory that says our universe, just after the Big Bang, didn't just grow, it exploded outward faster than light itself. In a fraction of a second, space stretched, smoothing out any wrinkles, creating the uniform cosmos we see today. Scientists like Alan Guth proposed this idea to explain why the universe looks so even, why galaxies are spread so smoothly across the sky. The cosmic microwave background, that faint glow we explored earlier, carries the imprint of this rapid expansion, its tiny ripples evidence of a universe stretched flat. But here's where the story grows wilder. Some scientists believe inflation didn't stop everywhere at once. In certain pockets, it slowed, forming bubbles of space where galaxies and stars could form, like ours. Yet, elsewhere, inflation continues, a ceaseless storm of expansion, birthing new bubbles endlessly. Each bubble is a universe, a world with its own beginning, its own physics, glowing softly in the vastness. Now, imagine those bubbles, each one a universe, floating in this cosmic sea, their surfaces shimmering like soap bubbles catching the light. This is the heart of eternal inflation, a theory that suggests our universe is just one of many, each born when a patch of inflating space settles into a lower energy state. These bubbles form through quantum fluctuations, tiny ripples in the energy field that drove inflation, called the inflaton field. Think of this field as a restless ocean, occasionally dipping low enough to create a pocket of calm, a place where a universe can begin. Each bubble universe expands on its own, separated by vast stretches of still inflating space, moving apart faster than light can travel. This means we can't see these other universes. They're light forever out of reach, like lanterns glowing on a distant shore. Scientists like André Linde, who developed this idea, suggest that these bubbles could number in the billions, each one a cosmos with its own stars, planets, and perhaps life, all unique in their design. Let's linger on this image, as if you're drifting among these bubbles, each one a world unto itself. What makes eternal inflation so mesmerizing is that each bubble universe could have its own physical laws. In our universe, gravity pulls, atoms form, and stars burn with a familiar rhythm. But in another bubble, gravity might be weaker or stronger, reshaping how matter gathers. The constants that govern our physics, like the strength of the electromagnetic force or the mass of a proton, might shift, creating worlds where stars never ignite or atoms can't hold together. Some bubbles might collapse moments after forming, too unstable to endure. Others could host entirely new forms of matter, energies, or even dimensions we can't imagine. Scientists explore these possibilities through mathematics, modeling how different constants might shape a universe. The idea is like a cosmic library, each book a different universe, written in a language of physics we may never read, yet endlessly fascinating in its variety. Now, shift your mind to a quiet corner of this multiverse, where each bubble tells a unique story. The reason we can't see these other universes lies in the nature of inflation itself. The space between bubbles expands so rapidly that light from one can't reach another, like ships sailing apart on an infinite sea. Yet, scientists wonder if there might be traces of these other worlds in our own. Some propose that if two bubbles collided in the distant past, their meeting could leave a mark, a faint ripple in the cosmic microwave background. Researchers have searched for such signs, using telescopes to study the sky for unusual patterns, like a circular scar where another universe brushed against ours. One curious feature, called the cold spot, a slightly cooler patch in the cosmic microwave background, has sparked debate. Could it be the echo of another universe's touch? While no definitive proof exists, the search continues, a quiet quest for clues to a multiverse hidden just beyond our sight. Imagine now a universe where the laws of physics allow entirely different possibilities, like stars that sing in colors we can't see, or planets that drift without gravity's pull. The multiverse theory suggests that our universe is finely tuned for life, not because it was designed that way, but because it's one of many where conditions just happen to be right. This is called the anthropic principle. We exist in a universe where life is possible because only such universes can host observers like us. In other bubbles, where physics is less forgiving, no one might be there to wonder. Scientists like Stephen Hawking explored this idea, noting that our universe's constants seem almost too perfect for stars, planets, and life to form. The multiverse offers an answer. With countless universes, some are bound to have the right recipe, like a cosmic bakery producing every possible flavor of cake. This thought is soothing in its vastness, a reminder that our existence is a rare and beautiful note in an infinite symphony. Let's pause here, your thoughts drifting like a leaf on a gentle stream. The multiverse isn't just a scientific idea, it's a philosophical one, asking us to rethink our place in reality. If other universes exist, they might be closer than we think, separated not by distance, but by the barriers of inflating space. Some could mirror our own, with galaxies and stars like ours, while others might be alien, with physics so strange that matter itself behaves differently. Scientists can't directly observe these other bubbles, but they use models to predict what they might be like, drawing on quantum field theory to understand how inflation works. The math suggests that new universes are born endlessly, each one a new experiment in cosmic creativity. This idea is like a soft glow in the mind, a reminder that our universe is part of something larger, a vast dance of possibilities that stretches beyond imagination. Now, picture a cosmic nursery, where universes are born like bubbles rising in a quiet pond. The process of eternal inflation is self-perpetuating, like a fire that never stops sparking new flames. Each bubble forms when a quantum fluctuation shifts the inflaton field, creating a pocket where expansion slows, allowing matter and energy to settle into familiar forms. But the space between these bubbles keeps inflating, pushing them apart, creating more room for new universes to emerge. Scientists study this through complex equations, trying to understand how these fluctuations shape the cosmos. The beauty of this idea lies in its endlessness. There's no limit to how many universes might exist, each one a new story, a new set of rules. It's like a cosmic garden, where every seed grows into a different world, each blooming in its own way, a thought that feels both grand and calming. As we drift through this sea of bubbles, consider the possibility that our universe is just one of many, a single note in a chorus that never ends. Scientists have yet to find direct evidence of the multiverse, but the theory of inflation, supported by observations of the cosmic microwave background, lends it weight. The uniformity of our universe, its flatness, and the patterns in its oldest light all hint at a process like inflation, which could naturally lead to a multiverse. Researchers continue to probe these ideas, using telescopes and particle accelerators to search for clues, like ripples or anomalies that might suggest another universe's presence. The thought of countless worlds, each with its own stars and stories, is like a gentle wave, washing over you with a sense of wonder, inviting you to rest in the vastness of the unknown. Let's carry this wonder forward, as if you're gliding from one bubble to another, each shimmering with possibility. The multiverse raises a new question. If other universes exist, could something connect them, bridging the vast gulfs of inflating space? What if there were pathways, hidden tunnels through the fabric of reality, linking one cosmos to another? Let's let this idea guide us into the next part of our journey, where we'll explore the concept of wormholes, cosmic bridges that might lead beyond our universe to places we can only dream of. Take a slow breath and let your mind float toward this new mystery, waiting just beyond the shimmering veil of our cosmic bubble. We've drifted through the shimmering sea of bubble universes, each one a cosmos glowing with its own unique stars, separated by the vast expanse of eternal inflation. Now, let's glide gently toward a new mystery, where the fabric of space itself might hold secret pathways. Take a slow, deep breath and picture a glowing bridge of light, shimmering like a silver thread stretched across the void. This is the idea of a wormhole, a tunnel through the very structure of space and time, a cosmic shortcut that could connect distant corners of our universe, or even lead to another entirely. We're about to explore these theoretical passages, born from the equations of physics, that might weave together the tapestry of the multiverse. Let this thought settle softly, like a whisper from the cosmos, as we wander into the enigma of wormholes and the bridges they might form beyond our universe's edge. Imagine a sheet of cosmic silk, smooth and vast, representing the space we live in, dotted with stars and galaxies like delicate embroidery. Now, picture folding that sheet so two distant points touch, and a tunnel forms between them, bypassing the long journey across the surface. This is the essence of a wormhole, a concept that emerges from Albert Einstein's theory of general relativity. In 1935, Einstein and Nathan Rosen described a mathematical solution called the Einstein-Rosen bridge, a tunnel linking two points in space-time. These bridges don't just connect places within our universe. They could, in theory, link to another universe entirely, like a hidden door in the cosmic architecture. Scientists envision wormholes as narrow throats, perhaps only a few atoms wide, with entrances that might look like black holes but lead somewhere else. The idea is like a quiet melody, suggesting that the universe might be threaded with secret passages, waiting to be discovered in the stillness of the night. Now, shift your mind to a starlit path, where the tunnel of a wormhole glows faintly, its edges shimmering with the energy of the cosmos. For a wormhole to exist, it needs more than just the bending of space-time. It requires something extraordinary to hold it open. In physics, this is called exotic matter, a substance with negative energy that defies the usual rules of gravity and pressure. Unlike ordinary matter, which pulls things together, exotic matter pushes outward, keeping the wormhole's throat from collapsing. Scientists have seen hints of such strange energy in quantum effects, like the Casimir effect, where tiny plates in a vacuum are pushed together by invisible forces. But creating enough exotic matter to stabilize a wormhole large enough for anything to pass through remains a dream, a challenge for future minds. The thought of these tunnels, fragile yet possible, is like a soft glow in the distance, a beacon of mystery that invites quiet contemplation. Picture now a cosmic traveler, standing at the mouth of a wormhole, its entrance a swirling vortex of light and shadow. If wormholes exist, they could connect not just distant galaxies but entirely different universes, each with its own laws of physics. Some scientists speculate that a wormhole's far end might open into a bubble universe from the multiverse we explored, a place where gravity works differently or stars burn in unfamiliar colors. The math of general relativity allows for such connections, but there's a catch. Wormholes are unstable. An Einstein-Rosen bridge, for example, would collapse almost instantly, too fleeting for even light to pass through. To make a wormhole traversable, it would need to be propped open by that exotic matter, a substance so rare and strange, it might only exist in the realm of theory. The idea of stepping through such a portal, crossing into another reality, is like a gentle ripple in a pond, stirring the imagination with possibilities that feel both distant and close. Let's linger on this image, as if gazing into the swirling depths of a wormhole's entrance, its light flickering like a candle in the cosmic night. Scientists have explored wormholes not just as shortcuts, but as potential clues to the nature of reality itself. In the 1982nd, physicist Kip Thorne and his colleagues studied whether wormholes could be used for time travel, linking not just spaces, but moments in time. Their work suggested that a stable wormhole might allow a traveler to emerge before they entered, creating paradoxes that challenge our understanding of cause and effect. To prevent such contradictions, some physicists propose the chronology protection conjecture, suggesting that quantum effects might close off any time-traveling wormholes, like a cosmic gatekeeper ensuring order. This interplay of possibility and constraint is like a soft lullaby, weaving a sense of wonder with the comfort of limits, guiding you toward a peaceful rest. Now, imagine a universe where wormholes are not just theoretical but part of its hidden structure, like veins running through the body of the cosmos. Some scientists suggest that tiny, quantum-scale wormholes might exist at the smallest levels of reality, in the frothy foam of space-time where particles flicker in and out of existence. These microscopic tunnels, far too small for anything to pass through, could be a fundamental part of the universe's fabric, connecting points in ways we can't yet measure. Researchers at places like CERN, with its particle accelerators, search for hints of these quantum effects, hoping to find traces of energies that might suggest such connections. The idea of a universe laced with these tiny bridges is like a delicate web, each thread a possibility, shimmering in the quiet of the night, inviting you to dream of what lies beyond. Shift your thoughts now to a grander vision, where a wormhole's entrance glows near a black hole, its gravity bending light into a halo of mystery. Some theories propose that black holes themselves might be linked to wormholes, their singularities points of infinite density, acting as gateways to other regions of space, or even other universes. Unlike the black holes we know, which crush matter into oblivion, a wormhole's passage might lead to a white hole, a theoretical opposite that spews out light and matter. This idea, while speculative, comes from the same equations that describe black holes, suggesting that the universe might hide exits where we least expect them. Scientists like Stephen Hawking have explored these possibilities, wondering if the information swallowed by black holes might escape through such tunnels to another reality. The thought is like a distant star, twinkling with promise, yet too far to touch, a gentle reminder of the cosmos's endless secrets. Let's pause here, as if standing at the threshold of a wormhole, its light casting soft shadows across the void. The search for wormholes is a quest for the unknown, driven by mathematics and imagination. Scientists use general relativity to model these tunnels, but detecting them is another matter. If a wormhole exists, its entrance might look like a gravitational lens, bending the light of stars behind it in a distinctive way. Astronomers scan the sky for such anomalies, using telescopes to search for signs of warped space. So far, no wormholes have been found, but the possibility remains, like a hidden path waiting to be uncovered. The idea of these cosmic bridges, connecting the unimaginable, is like a quiet song, its notes drifting through the night, soothing you with the thought that the universe might be more connected than it seems. Now, picture a universe where wormholes are not just passages but part of a larger network, linking our cosmos to others in the multiverse. If such connections exist, they could redefine what we mean by the edge of the universe. Instead of a boundary, the edge might be a gateway, a place where our reality touches another. Some physicists speculate that wormholes could be stabilized by forces we don't yet understand, perhaps tied to quantum gravity or the energies of the early universe. Experiments at particle accelerators and observations of gravitational waves, like those detected by LIGO, might one day reveal hints of these tunnels, ripples in space-time that carry echoes of distant realities. The thought of a universe woven with such pathways is like a gentle current, carrying you toward a sense of wonder, a cosmos full of hidden doors waiting to be explored. As we rest in this moment, the idea of wormholes invites us to imagine a universe not isolated but interconnected, a tapestry of tunnels linking stars, galaxies, and perhaps entire realities. The science of wormholes is still young, a blend of bold ideas and rigorous equations, yet it holds a quiet promise that the edge of our universe might not be an end, but a beginning. Let's carry this thought forward, gliding from the shimmering bridges of wormholes to a new mystery, where the universe might hide extra dimensions, folded and unseen, shaping the very laws of reality. Take a slow breath and let your mind drift toward this next chapter, where the cosmos reveals its hidden layers, waiting just beyond the glow of our cosmic bridges. We've wandered through the shimmering bridges of wormholes, those elusive tunnels that might connect distant corners of our universe, or even lead to another. Now, let's drift gently into a stranger realm, where the very fabric of reality hides dimensions beyond our everyday senses. Take a slow, deep breath and picture yourself passing through a gossamer veil, its threads woven from starlight, revealing a universe not just of height, width, and depth, but of hidden layers folded into the smallest spaces. This is the world of extra dimensions, a concept from string theory that suggests our universe might be a thin slice of a grander, multi-dimensional tapestry. Let's explore these hidden realms, where the laws of physics take shape in ways we can scarcely imagine, as the cosmos hums a quiet lullaby of mystery. Imagine a world where directions exist, beyond up, down, left or right, like secret notes in a cosmic melody we can't hear. String theory, a framework aiming to unite gravity with the quantum world, proposes that the universe doesn't just have the three spatial dimensions we experience, nor the single dimension of time, but as many as 10 or 11 dimensions in total. These extra dimensions aren't sprawling like the ones we know. They're curled up, impossibly small, tucked into spaces far tinier than an atom. Scientists call these compactified dimensions, and they might exist at every point in our universe, like hidden folds in a piece of silk. These folds, known as Calabi-Yau manifolds, are complex shapes with intricate geometries, each curve and twist determining how particles and forces behave. The idea is like a quiet whisper, suggesting that the universe's deepest secrets are woven into spaces too small to see, yet ever present around us. Now, picture a cosmic tapestry, its threads vibrating with the energy of creation, each vibration a note in the universe's song. In string theory, everything electrons, photons, Even gravity arises from tiny, vibrating strings, like the strings of a guitar playing different tunes. The way these strings vibrate depends on the shape of those hidden dimensions. If the extra dimensions are curled one way, a string might vibrate to form an electron. Curled another, it might become a quark or a photon. This means the laws of physics, the constants that govern our world, are shaped by these invisible realms. Scientists like Edward Witten have explored how these dimensions could explain why gravity is so much weaker than other forces, like electromagnetism. Perhaps gravity spreads into these extra dimensions, diluting its strength in our three-dimensional slice. The thought is like a soft glow, illuminating the idea that our reality is just one verse in a multi-dimensional symphony. Let's linger on this vision, as if you're gazing into a kaleidoscope of cosmic patterns, each twist revealing a new shape of reality. The extra dimensions in string theory are so small, billions of times smaller than a proton, that we can't see or feel them. Yet, they might hold the key to understanding why our universe works the way it does. For example, the strength of the strong nuclear force which binds atoms together could depend on the geometry of these hidden spaces. If those dimensions were shaped differently, stars might not burn, or atoms might not form at all. Scientists test these ideas at places like the Large Hadron Collider, smashing particles together to look for signs of energy leaking into extra dimensions. So far, no such leaks have been found, but the search continues, like a quiet quest for the hidden notes that define our cosmos, a melody that soothes with its mystery. Now, shift your mind to a grander scene, where our universe is a thin membrane floating in a vast, higher dimensional space called the bulk. This idea comes from a branch of string theory called brain-world cosmology, where our three-dimensional world is a brain, a kind of cosmic sheet, suspended in a larger reality. Other brains, each a universe with its own physics, might float nearby, separated by distances too small or too strange for us to cross. Gravity, unlike other forces, could move through the bulk, connecting our brain to others. This might explain why gravity feels so weak, because it's spread across dimensions we can't access. Scientists like Lisa Randall have studied how these extra dimensions could influence our universe, perhaps leaving subtle traces in the way particles behave. The image is like a delicate web, each thread a universe, shimmering in a higher dimensional night, inviting quiet wonder. Picture now a cosmic orchestra, where each instrument plays a note shaped by these hidden dimensions, creating the harmony of our reality. The extra dimensions might not just be small. Some theories suggest a few could be large, stretching across vast distances, yet invisible to us because we're confined to our three-dimensional brain. Light, matter, and most forces are stuck to our brain, like water droplets on a leaf, unable to move into the bulk. But gravity, ever elusive, might wander freely, carrying whispers of other worlds. Experiments at particle accelerators search for these whispers, looking for particles that vanish into extra dimensions or unexpected patterns in collisions. The idea that our universe is just one layer in a multi-dimensional cosmos is like a soft breeze, carrying the scent of possibilities too vast to grasp, yet comforting in their mystery. Let's pause here, as if you're resting on a silken thread, suspended in the vastness of this multi-dimensional tapestry. The concept of extra dimensions challenges our sense of reality, suggesting that what we see is only a shadow of a deeper truth. Scientists use mathematics to explore these ideas, crafting equations that describe how strings vibrate in 10 or 11 dimensions. These equations, part of M-theory, a unified version of string theory, suggest that the extra dimensions could take countless shapes, each one birthing a different universe with its own rules. Some might have no gravity, others no light, and some might host life in forms we can't imagine. The thought is like a gentle wave, washing over you with the idea that our universe is a single note in a grand, multidimensional chord, played across the cosmos. Now, imagine a universe where these extra dimensions aren't just hidden, but active, shaping the very birth of reality. In the early universe, during the fiery moments after the Big Bang, these dimensions might have played a role in setting the stage for everything we know. Some scientists propose that the rapid expansion of inflation, which we explored earlier, was driven by the dynamics of these extra dimensions, unfolding like petals in a cosmic flower. The shapes of these dimensions could have determined how matter formed, how galaxies clustered, and even how time itself flows. Researchers look for clues in the cosmic microwave background, hoping to find patterns that hint at the influence of higher dimensions. The idea is like a soft light, glowing with the possibility that our universe is a delicate balance, shaped by realms we can't yet touch, yet ever present in the fabric of reality. As we drift through this multidimensional cosmos, consider the possibility that these extra dimensions are not just a theoretical curiosity, but a fundamental part of existence. If they exist, they could explain mysteries like the unification of forces, why gravity behaves differently, or even why our universe seems so perfectly tuned for life. Scientists are building new experiments, like more powerful particle accelerators or gravitational wave detectors, to search for signs of these dimensions. They hope to find anomalies, particles moving in unexpected ways, or energies that don't add up that might suggest a leak into the bulk. The thought of a universe woven with hidden layers is like a quiet song, its notes blending into a harmony that soothes the mind, inviting you to rest in the vastness of its mystery. Let's carry this wonder forward, as if you're gliding through a veil of light, each thread a dimension beyond our own. The idea of extra dimensions opens a new question. What if our universe's birth wasn't a single event, but part of a cycle, a cosmic heartbeat that pulses through time? Let's let this thought guide us into the next part of our journey, where we'll explore the Big Bounce, a theory that suggests the universe might collapse and be reborn over and over in an eternal rhythm. Take a slow breath and let your mind drift toward this new mystery, waiting just beyond the hidden folds of our multidimensional cosmos. We've glided through the hidden folds of extra dimensions, where the universe's deepest secrets might be tucked away in realms too small to see. Now, let's drift into a new cosmic story, where the universe itself breathes in an eternal rhythm. Take a slow, deep breath and imagine the cosmos as a vast, living flame, flickering and fading, only to blaze anew. This is the Big Bounce, a theory that suggests our universe doesn't begin or end, but pulses through cycles of collapse and rebirth, like a phoenix rising from its own ashes. Let's explore this idea of a universe that renews itself, a cosmic cycle that redefines the edge of time, weaving a tale that hums with the quiet promise of eternity. Picture the universe as a great cosmic heart, beating through eons, each pulse a new beginning. The Big Bounce theory challenges the idea of a single Big Bang, proposing instead that our universe might have emerged from the collapse of a previous one. In this model, space and time don't start from a singular point of infinite density but transition through a moment of extreme compression called a bounce. Scientists like Paul Steinhardt and Neil Turok have explored this idea, suggesting that the universe contracts under its own gravity, shrinking to a dense state before springing outward again in a new expansion. This cycle could repeat endlessly, each phase lasting billions or even trillions of years. The cosmic microwave background, that faint glow from the universe's infancy, might carry echoes of these past cycles, like ripples left by a stone long sunk in a quiet pond. The thought of a universe reborn over and over is like a gentle lullaby, singing of continuity across the vastness of time. Now, imagine a cosmic tapestry, woven not just with stars but with the threads of countless universes, each one a chapter in an eternal story. The Big Bounce comes from a field called loop quantum cosmology, which suggests that space and time aren't smooth at the smallest scales, but made of tiny, discrete loops, like the weave of a fabric. When the universe collapses, these loops prevent it from reaching infinite density, avoiding the singularity that marks the limit of traditional physics. Instead, the universe rebounds, like a ball hitting the ground and bouncing upward. This bounce creates a new expansion, a fresh canvas for galaxies, stars, and planets to form. Scientists study this through mathematical models, trying to understand how quantum effects could smooth the transition from collapse to rebirth. The idea is like a soft wave, carrying the promise of renewal, a universe that never truly ends but transforms in a quiet, cosmic dance. Let's linger on this vision, as if you're gazing at a star that burns out, only to reignite in a new sky. The Big Bounce solves some of the deepest puzzles in cosmology, like why our universe appears so flat and uniform. In the traditional Big Bang model, inflation explains this by stretching space rapidly, But the bounce offers another path. The slow contraction before a bounce can smooth out irregularities, setting the stage for a universe that looks even across vast distances. Researchers look for clues in the cosmic microwave background, searching for patterns that might hint at a previous collapse. Some propose that subtle variations in its temperature could be traces of a universe before ours, like footprints left in cosmic sand. The thought of a universe that carries memories of its past lives is like a gentle breeze, stirring the imagination with the possibility of an eternal cycle, soothing in its timeless rhythm. Now, shift your mind to a scene where the universe contracts, stars dimming as space draws inward, only to burst forth in a new dawn. In the Big Bounce model, each cycle might not be identical. The laws of physics could shift slightly with each bounce, creating universes with different constants or forces. One cycle might birth a universe like ours, with galaxies and life, while another might produce a cosmos where gravity repels or stars never form. Scientists explore these possibilities through simulations, modeling how quantum gravity might influence each bounce. The idea that our universe could be one of many in a chain of cosmic rebirths is like a quiet river, flowing through time, carrying stories of worlds that came before and those yet to come. This vision of continuity, of a universe that reinvents itself, offers a sense of calm, like a heartbeat echoing through eternity. Picture now a cosmic clock, its hands turning not in hours but in epochs, each tick marking the birth of a new universe. The Big Bounce challenges our sense of beginnings and endings, suggesting that time itself might be cyclical, a loop rather than a straight line. In this model, the Big Bang we know wasn't the start of everything but a transition, a moment when the universe flipped from collapse to expansion. Scientists like Roger Penrose, who proposed a related idea called conformal cyclic cosmology, suggest that the end of one universe might blend seamlessly into the beginning of another, with no clear boundary. They look for evidence in the cosmic microwave background, hoping to find rings or patterns that could be relics of a previous cycle. The idea is like a soft melody, its notes blending into one another, creating a sense of peace in the thought that the universe is never truly lost, only reborn. Let's pause here, as if you're floating in the quiet space between cosmic cycles, where time folds into itself. The Big Bounce also addresses the singularity problem, where traditional physics breaks down at the universe's origin. In a singularity, density becomes infinite, and equations fail, like a book with missing pages. Loop quantum cosmology avoids this by setting a minimum scale for space and time, ensuring the universe never reaches infinite density. This makes the bounce a smoother process, a gentle shift rather than a violent break. Researchers test these ideas through mathematical models, hoping to predict how the bounce might leave traces in the universe's structure, like the way galaxies cluster or the patterns in cosmic radiation. The thought of a universe that flows through cycles, each one a new chapter, is like a gentle tide, washing over you with the promise of renewal, inviting quiet reflection. Now, imagine a universe where each cycle leaves a faint imprint, like a shadow cast by a previous world. Some scientists, like Penrose, suggest that the end of one universe could carry information into the next, encoded in the patterns of light or gravity. These imprints might appear as subtle anomalies in the cosmic microwave background, like whispers from a cosmos long gone. Researchers use powerful telescopes to search for these signs, hoping to uncover evidence of a cycle before our own. The idea that our universe might hold memories of its past is like a soft light, glowing with the possibility that we're part of something larger, a story that stretches beyond time itself. This vision of a cyclical cosmos, where endings are beginnings, offers a sense of calm, a universe that cradles its own history in a quiet, eternal embrace. As we drift through this cyclical cosmos, consider the philosophical weight of a universe without a true beginning. The Big Bounce suggests that time might not have a starting point, but flows in a circle, each cycle a new verse in an endless poem. Scientists explore this through theories like M-theory, which ties the bounce to the extra dimensions we've discussed, suggesting that these hidden realms could influence how the universe contracts and expands. The interplay of quantum gravity and cosmic cycles is like a delicate dance, each step a balance of forces we're only beginning to understand. The thought that our universe might be one of many in a chain of rebirths is like a quiet song, its notes blending into a harmony that soothes the mind, inviting you to rest in the vastness of eternity. Let's carry this gentle rhythm forward, as if you're gliding from one cosmic cycle to another, each pulse a new beginning. The Big Bounce opens a new question. What if the universe's edge isn't a place or a time, but a boundary of information, a surface that holds the story of everything within it? Let's let this thought guide us into the next part of our journey, where we'll explore the holographic principle, the idea that our universe might be a projection, a cosmic painting on a two-dimensional canvas. Take a slow breath and let your mind drift toward this new mystery, waiting just beyond the eternal heartbeat of our reborn cosmos. We've drifted through the eternal rhythm of the Big Bounce, where the universe pulses like a cosmic heart, reborn in endless cycles. Now, let's glide into a stranger, more mesmerizing idea, where reality itself might be a projection, a shimmering image cast on a distant screen. Take a slow, deep breath and picture a vast, glowing canvas, its surface painted with every star, galaxy, and moment of time, yet all contained within a single, flat boundary. This is the holographic principle, a theory that suggests our three-dimensional universe might be encoded on a two-dimensional surface at its edge, like a cosmic painting that captures all of existence. Let's explore this mind-bending idea, where the edge of the universe becomes not a place but a code, a quiet whisper of information that holds the secrets of everything we know. Imagine holding a shimmering hologram, like the ones on a credit card, where a flat surface sparkles with the illusion of depth, stars and planets dancing in 3 dimensions. The holographic principle, proposed by physicists like Gerard T. Hooft and Leonard Susskind in the 1992nd, suggests that our entire universe works this way. All the matter, energy, and events we experience, every galaxy, every breath, could be encoded as information on a two-dimensional boundary, perhaps at the cosmic horizon we explored earlier. This boundary, 46 billion light-years away, might act like a cosmic screen, holding every detail of our three-dimensional reality in a flat, intricate pattern. The idea comes from studying black holes, where physicists like Jacob Bekenstein found that a black hole's entropy, a measure of its information, depends not on its volume, but on the surface area of its event horizon. This discovery, like a soft glow in the night, hints that the universe itself might be a projection, a hologram woven from information at its edge. Now, picture a cosmic library, its shelves not filled with books, but with a single vast page, inscribed with the story of everything. The holographic principle suggests that the information needed to describe our universe, every particle, every force, fits onto this two-dimensional surface. Each bit of information, smaller than the tiniest speck, encodes a piece of reality, like a pixel in a cosmic image. This idea grew stronger with the ADS CFT correspondence, a breakthrough by one Maldacena in 1997, which showed that a universe with gravity in a curved space, called anti-de Sitter space, can be fully described by a simpler, flat theory without gravity on its boundary. Though our universe isn't exactly like this space, the correspondence offers a clue. Perhaps our reality is a projection of a deeper, flatter truth. The thought is like a gentle ripple, spreading across a quiet pond, suggesting that the universe's depth is an illusion, yet one that sparkles with meaning. Let's linger on this vision, as if gazing into a cosmic mirror, its surface reflecting every moment of existence in a single glance. The holographic principle challenges our sense of reality, proposing that the 3 dimensions we navigate, height, width, depth, are not fundamental but emergent, like shadows cast by a distant light. This idea stems from black holes, where the information about everything that falls in is stored on their surface, not lost in their depths. Scientists like Stephen Hawking wrestled with this, showing that information isn't destroyed but preserved in a way that defies our intuition. If a black hole's contents can be encoded on its boundary, perhaps our entire universe follows the same rule, with every star and galaxy a projection of data at the cosmic edge. Researchers study this through mathematical models, exploring how quantum mechanics and gravity intertwine to create this holographic effect, like a soft melody weaving the fabric of reality. Now, shift your mind to a starlit gallery, where the universe is displayed as a vast, two-dimensional artwork, each brushstroke a moment in time. The holographic principle suggests that the edge of the universe, that cosmic horizon, isn't just a limit of light, but a surface that holds all knowledge of our reality. Every event, from the birth of a star to the flicker of a thought, could be written in a cosmic code, stored in patterns too intricate to see. Scientists explore this through string theory, which we touched on earlier, where tiny strings vibrate to create particles and forces. These vibrations might be governed by the information on this boundary, like notes played on a cosmic harp. The idea that everything we know could be encoded in two dimensions is like a quiet whisper, suggesting that reality is simpler, yet more mysterious than it seems, a thought that soothes with its elegance. Picture now a universe where every detail is a reflection, like moonlight dancing on a still lake. The holographic principle implies that the volume of space we live in, its stars, planets, and vast voids, might be a projection from a flatter, more fundamental reality. This raises profound questions. If our universe is a hologram, what lies beyond the boundary? Is there a deeper reality, a higher dimensional space where the true information resides? Scientists like Leonard Susskind propose that this boundary could be at the cosmic horizon, where light's journey ends, or even at an abstract edge defined by the limits of information itself. Researchers look for clues in the cosmic microwave background, hoping to find patterns that match the predictions of holographic models, like subtle ripples that hint at a two-dimensional code. The thought is like a soft light, illuminating the idea that our universe is a delicate projection, a cosmic dream painted on a distant canvas. Let's pause here, as if resting before a glowing tapestry, its threads woven with the essence of reality. The holographic principle also connects to quantum gravity, the quest to unite Einstein's theory of space-time with the strange rules of the quantum world. In a holographic universe, gravity itself might be an illusion, emerging from the interactions of particles on the boundary, like shadows dancing from a hidden source. Scientists explore this through experiments and theories, like those tested at particle accelerators, searching for signs that our reality is governed by a flatter quantum framework. The ADS-CFT correspondence offers a mathematical bridge, showing how a universe with gravity can mirror a simpler, gravity-free system. This idea, like a gentle current, carries the promise that the universe's deepest truths might be encoded in a way that's both simple and profound, inviting quiet contemplation. Now, imagine a cosmic stage where the drama of existence plays out not in three dimensions, but as a projection from a two-dimensional script. The holographic principle suggests that the edge of the universe isn't a physical barrier, but a surface of information, holding every detail of our reality in its embrace. This boundary might not be a place we can travel to, but a limit of what we can know, like a book that contains every story yet fits on a single page. Scientists study this through the entropy of black holes, which measures how much information they can hold, finding that it scales with surface area, not volume. This insight, born from decades of work by physicists like Hawking, points to a universe where information is the true essence, a quiet truth that underlies everything we see. The thought is like a soft breeze, carrying the idea that reality is a delicate balance of code and wonder, soothing in its mystery. As we drift through this holographic cosmos, consider the philosophical weight of a universe that's a projection. If everything we know is encoded on a distant surface, what does it mean for our sense of reality? Are we shadows of a deeper truth, or is the hologram as real as anything we touch? Scientists ponder this through models of quantum gravity, hoping to find connections between the holographic principle and the early universe, perhaps in the patterns of cosmic radiation or the behavior of particles. The idea that our three-dimensional world might be a reflection of a simpler two-dimensional code is like a quiet song, its notes blending into a harmony that soothes the mind, inviting you to rest in the vastness of this cosmic mystery. Let's carry this gentle vision forward, as if gliding from a holographic canvas to a new realm of wonder, where the universe might mirror another in perfect symmetry. The holographic principle opens a new question. What if our universe is balanced by another, a mirror image where time and matter flow in reverse? Let's let this thought guide us into the next part of our journey, where we'll explore the idea of an anti-universe, a cosmic twin that balances our reality across the divide of time. Take a slow breath and let your mind drift toward this new mystery, waiting just beyond the shimmering surface of our holographic cosmos. We've drifted through the shimmering canvas of the holographic principle, where the universe might be a projection, a delicate image encoded on a distant boundary. Now, let's glide into an even stranger realm, where time itself might mirror another reality. Take a slow, deep breath and picture a cosmic river, its waters flowing in two directions, one side carrying our universe forward, the other a reflection moving backward. This is the idea of an anti-universe, a theoretical twin to our cosmos, where time runs in reverse and matter is replaced by its opposite, antimatter. Let's explore this concept of a mirror universe, born from the same cosmic event as ours, balanced across a point of perfect symmetry, like a quiet melody echoing through the vastness of eternity. Imagine a moment at the dawn of existence, a single point of balance where time and matter stood still, like the calm center of a spinning wheel. The anti-universe theory suggests that the Big Bang wasn't just the birth of our universe, but also of its mirror image, a cosmos where time flows backward and every particle is replaced by its antimatter counterpart. In our universe, matter dominates electrons, protons, the building blocks of stars and planets. But antimatter, with opposite charges, like positrons instead of electrons, should have been created in equal amounts at the Big Bang. Scientists puzzle over why our universe favors matter, a mystery called baryon asymmetry. The anti-universe offers a poetic solution. Perhaps the antimatter didn't vanish but exists in a mirror cosmos, moving backward through time. This idea, rooted in the symmetry of physics, is like a soft reflection in a cosmic lake, suggesting our reality is only half of a grander design. Now, picture a universe where stars burn in reverse, their light converging back into their cores, as time unwinds toward its origin. The anti-universe is tied to a fundamental concept in physics, called CPT symmetry, which stands for charge, parity, and time. This symmetry says that if you reverse a particle's charge, flip its spatial orientation, and run time backward, the laws of physics should remain unchanged. Some cosmologists, like those exploring theories beyond the standard model, propose that our universe and its anti-universe form a balanced pair, born together at the Big Bang, each moving in opposite temporal directions. In this mirror cosmos, what we see as the future would be their past, yet their physics would feel as natural to them as ours does to us. The idea is like a gentle ripple spreading across a quiet pond, hinting that our reality might be mirrored by another, perfectly balanced, yet forever out of reach. Let's linger on this vision, as if gazing into a cosmic mirror, its surface reflecting a universe that's both familiar and alien. The anti-universe could explain why our cosmos has so little antimatter. When the Big Bang occurred, it might have split matter and antimatter into two separate realms, each evolving along its own timeline. In our universe, particles like electrons and protons form atoms, stars, and galaxies. In the anti-universe, positrons and antiprotons might do the same, creating their own cosmic tapestry, but with time flowing backward. Scientists study this through experiments at places like CERN, where particle accelerators smash particles together to create tiny amounts of antimatter, hoping to understand why it's so rare here. The thought that our universe might have a twin, living in reverse, is like a soft whisper, carrying the promise of symmetry, a balance that soothes with its elegance. Now, shift your mind to a scene where two universes meet, not in space but at a single moment of cosmic birth, like two sides of a folded page. The anti-universe theory suggests that the Big Bang was a point of symmetry, not a beginning but a pivot, where time diverged in two directions. Our universe expands forward, galaxies drifting apart, stars igniting and fading. In the anti-universe, the opposite might unfold, galaxies converging, stars unforming, as if the cosmos is rewinding to its origin. This doesn't mean chaos. Their inhabitants, if they exist, would experience time as naturally as we do, their memories of the past and hopes for the future mirroring ours in reverse. Scientists explore this through mathematical models, checking if the laws of physics hold under such symmetry. The idea is like a quiet stream, flowing gently in two directions, inviting you to ponder a universe that's both opposite and equal to our own. Picture now a cosmic balance, where our universe and its anti-universe are like two dancers, moving in perfect harmony across a shared stage. The concept of an anti-universe might also shed light on other mysteries, like the nature of neutrinos, ghostly particles that barely interact with matter. In our universe, neutrinos are left-handed, their spin aligned in a specific way, a peculiar asymmetry in the standard model of physics. Some scientists propose that right-handed neutrinos, which we've never seen, might belong to the anti-universe, balancing the cosmic equation. These particles could even be linked to dark matter, the invisible substance shaping galaxies. Experiments like those at the Deep Underground Neutrino Experiment search for clues, hoping to detect signs of these elusive particles. The thought of neutrinos as messengers between universes is like a faint star, twinkling with the possibility of connection, a gentle note in the cosmic symphony. Let's pause here, as if resting on the edge of this cosmic mirror, where two universes reflect each other in perfect symmetry. The anti-universe could also influence the cosmic microwave background, that ancient glow we've explored before. Some cosmologists suggest that subtle patterns or anomalies in its temperature might be echoes of this mirror realm, like shadows cast across time. For example, unexpected cold spots or alignments in the background radiation could hint at interactions between our universe and its twin. Researchers use telescopes to map these patterns, seeking signs that the Big Bang was a shared event, splitting reality into two mirrored halves. The idea that our universe might be entwined with another, separated only by the flow of time, is like a soft melody, its notes blending into a harmony that soothes with its balance. Now, imagine a universe where time's arrow points backward, yet life and light flourish just as they do here. The anti-universe theory doesn't just solve scientific puzzles, it reshapes our understanding of existence. If time runs backward, what we see as the expansion of our universe might be a contraction in theirs, yet both would feel natural to their inhabitants. This symmetry challenges our sense of now, suggesting that the present is only one perspective in a dual reality. Scientists explore this through quantum field theory, modeling how particles and forces might behave in a reverse timeline. The thought that our universe is part of a larger, balanced whole is like a gentle tide, washing over you with the promise of unity, a cosmos where every action has a mirror image, creating a quiet sense of harmony. As we drift through this mirrored cosmos, consider the possibility that the anti-universe isn't just a theoretical idea, but a necessary piece of the cosmic puzzle. The balance of matter and antimatter, the symmetry of time, and even the nature of dark matter might all find answers in this mirror realm. Scientists search for evidence in particle collisions, gravitational waves, and cosmic radiation, hoping to find traces of this hidden twin. The idea that our universe might be one half of a cosmic pair, each balancing the other, is like a soft light, glowing with the promise of a deeper truth, a reality where opposites complete each other. This vision of symmetry, where time and matter mirror each other across eternity, offers a sense of calm, a universe that's whole in its duality. Let's carry this gentle symmetry forward, as if gliding from a cosmic mirror to a new realm of wonder, where the earliest moments of the universe might still whisper to us. The anti-universe opens a new question. What if tiny particles, born in the first second of existence, carry messages from this mirrored reality, or even from the dawn of time itself? Let's let this thought guide us into the next part of our journey, where we'll explore the cosmic neutrino background, a sea of ghostly particles that might hold secrets from before the stars were born. Take a slow breath, and let your mind drift toward this new mystery, waiting just beyond the mirrored waters of our cosmic twin. We've glided through the mirrored waters of an anti-universe, where time flows backward, balancing our cosmos in a dance of perfect symmetry. Now, let's drift into an even older mystery, where whispers from the universe's first moments still linger. Take a slow, deep breath, and imagine a sea of ghostly particles, drifting silently through the cosmos, carrying secrets from a time before stars were born. This is the cosmic neutrino background, a faint echo of the universe's earliest seconds, born just after the Big Bang. Let's explore these elusive particles, invisible messengers that might hold clues to the dawn of existence, like a quiet lullaby woven from the threads of the cosmic past. Picture a universe in its infancy, a fiery chaos where light was trapped, unable to roam free. In those first moments, just a second after the Big Bang, the cosmos was a seething soup of particles, too hot and dense for atoms to form. Among these were neutrinos, tiny, nearly massless particles that barely interact with matter, slipping through stars and planets like whispers through a dream. Unlike light, which was scattered in the early universe's plasma, neutrinos broke free almost instantly, forming the cosmic neutrino background. This background, older than the cosmic microwave background we've explored, is a snapshot of the universe at 1 second old, a relic from a time when the cosmos was 1 billion degrees hot. Scientists estimate that trillions of these neutrinos pass through us every second, yet they're so elusive that detecting them is like catching a shadow in a storm. The thought is like a gentle hum, carrying the echo of a universe too young to shine, yet alive with possibility. Now, imagine a cosmic archive, its shelves filled not with books but with invisible particles, each one a page from the universe's first chapter. The cosmic neutrino background is incredibly faint, its neutrinos cooled by the universe's expansion to just a few degrees above absolute zero. This makes them vastly different from the high-energy neutrinos produced in stars or particle accelerators, which scientists can detect more easily. The relic neutrinos of the cosmic background move slowly, carrying memories of a time before light could travel freely. Researchers like those at the Princeton Tritium Observatory for Light, Early Universe, Massive Neutrino Yield, or Ptolemy, are designing experiments to capture these ghostly particles, using sensitive detectors to measure their faint interactions with rare isotopes like tritium. The idea is like a soft glow, illuminating the possibility that we might one day hear the universe's oldest whispers, a melody from the dawn of time. Let's linger on this scene, as if floating in a sea of neutrinos, each one a messenger from a time when the cosmos was newborn. These particles are special because they decoupled from the rest of the universe so early, just 1 second after the Big Bang, long before the cosmic microwave background formed at 380,000 years. This means they carry information about the universe's earliest moments, a time when matter and antimatter were still in balance, before the mysterious process that favored matter over its opposite. Scientists hope that studying the cosmic neutrino background could reveal clues about this asymmetry, explaining why our universe is filled with matter rather than nothing at all. The experiments are daunting, as neutrinos interact so weakly that detecting even one relic neutrino is a monumental challenge. Yet the pursuit is like a quiet quest, seeking a single note from a cosmic symphony that began billions of years ago. Now, shift your mind to a cosmic dawn, where the universe was a swirling cauldron of energy, and neutrinos were born in unimaginable numbers. The cosmic neutrino background is thought to be incredibly uniform, like a calm sea stretching across the cosmos, with slight variations that might hold secrets about the early universe. These variations could reveal details about the Big Bang itself, or even hints of events before it, if such a time exists. Some theories, like those tied to the Big Bounce or the anti-universe, suggest that neutrinos might carry imprints of previous cosmic cycles or mirrored realities. Scientists use mathematical models to predict how these neutrinos might affect the universe's structure, influencing the way galaxies form or the patterns in cosmic radiation. The thought is like a gentle breeze, carrying the idea that these invisible particles might hold the key to understanding the universe's deepest origins, a soothing mystery that whispers of eternity. Picture now a cosmic telescope, not for light but for neutrinos, its lens tuned to catch the faintest echoes of the universe's birth. Detecting the cosmic neutrino background is one of the greatest challenges in modern physics, requiring detectors far more sensitive than those used for other particles. Current experiments, like the IceCube Neutrino Observatory in Antarctica, catch high-energy neutrinos from cosmic events, but the relic neutrinos are far too weak for such tools. Instead, scientists propose using ultra-cold environments and rare materials, like tritium, to detect the subtle energy transfers caused by these ancient particles. The Ptolemy experiment, for example, aims to measure the tiny shifts in energy when neutrinos interact with atoms, a process so delicate it's like hearing a single drop of rain in a storm. The idea that we might one day touch the universe's first seconds is like a soft light, glowing with the promise of discovery, a quiet note in the cosmic melody. Let's pause here, as if resting in the silent sea of neutrinos, each one a relic of a time before stars. These particles might also shed light on other mysteries, like the nature of dark matter or the conditions of the early universe. Some scientists propose that neutrinos, with their tiny but non-zero mass, could contribute to the invisible mass-shaping galaxies, though they're not the whole story. Others suggest that the cosmic neutrino background could reveal whether the universe underwent exotic processes, like phase transitions or interactions with extra dimensions, in its earliest moments. Researchers model these possibilities using quantum field theory, trying to understand how neutrinos interacted with the primordial plasma. The thought that these ghostly particles might hold secrets from a time before light is like a gentle wave, washing over you with the promise of a deeper truth, a cosmos that speaks in whispers too soft to hear. Now, imagine a universe where neutrinos are the storytellers, their silent journeys weaving a tale of creation. The cosmic neutrino background is not just a scientific curiosity, but a window into a time when the universe was a different place, a realm of pure energy where the seeds of everything were sown. Scientists believe that studying these neutrinos could confirm predictions of the Big Bang, like the exact number of neutrino types 3, according to the Standard Model, or reveal new physics if unexpected patterns emerge. Experiments like KATYN, which measures neutrino mass, and future projects like Ptolemy aim to refine our understanding, inching closer to detecting these ancient relics. The idea that we might one day hear the universe's first whispers is like a quiet song, its notes blending into a harmony that soothes with its promise of discovery, a gentle reminder of how far we've come and how much lies beyond. As we drift through this sea of neutrinos, consider the philosophical weight of these particles, carrying secrets from a time we can barely imagine. The cosmic neutrino background challenges our sense of time, suggesting that the universe's earliest moments are still with us, woven into the fabric of reality. If we could detect these neutrinos, we might learn about the conditions that shape the cosmos, from the balance of matter and antimatter to the forces that drove inflation. Scientists are building new detectors, like those using liquid argon or ultra-pure materials, to catch the faint signals of these relics. The thought that the universe's first seconds might still speak to us is like a soft glow, illuminating the idea that we're connected to the cosmos's deepest past, a soothing link to the dawn of existence. Let's carry this gentle whisper forward, as if gliding from the sea of neutrinos to a new realm of wonder, where the search for these particles leads us to reflect on our place in the cosmos. The cosmic neutrino background opens a final question. What does it mean to be part of a universe so vast, with secrets so ancient, yet still unfolding? Let's let this thought guide us into the final part of our journey, where we'll reflect on the beauty and mystery of our cosmic home, and how these questions connect us to the infinite. Take a slow breath, and let your mind drift toward this closing chapter, waiting just beyond the ancient whispers of the cosmic neutrino background. We've drifted through the silent sea of neutrinos, those ghostly messengers whispering secrets from the universe's first seconds. Now, let's glide gently to the end of our cosmic journey, where we reflect on the vastness of these mysteries and our place within them. Take a slow, deep breath, and picture yourself floating in a boundless night sky, stars twinkling like lanterns in a quiet village, each one a story we've explored. This final chapter weaves together the threads of our adventure, from the edges of light to the possibilities of a multiverse, inviting you to ponder the beauty and wonder of the cosmos as you drift towards sleep. Let's linger in this moment, reflecting on what lies beyond the universe's edge and how these questions connect us to the infinite, like a soft lullaby sung by the stars. Imagine a cosmic tapestry, its threads woven from the light of distant galaxies, the vibrations of hidden dimensions, and the echoes of ancient particles. Our journey began with the observable universe, a sphere 93 billion light-years wide, defined by the light that has reached us since the Big Bang. We saw how this light, traveling for 13.8 billion years, carries stories from a time when the universe was young, a fiery cradle of creation. The cosmic horizon, that delicate boundary, marked not an end but a limit of time, a line where light's journey pauses. Scientists have mapped this horizon with telescopes like Hubble and James Webb, capturing photons from galaxies born in the universe's infancy, each one a chapter in a story that's still unfolding. The thought that our universe is but a glimpse of a larger reality is like a gentle breeze, carrying the promise of wonders yet unseen, a soothing reminder of the cosmos's vastness. Now, picture a quiet meadow under a starlit sky, each star a question about the universe's nature. We explored whether the cosmos is infinite, stretching endlessly like an ocean, or finite, curling back on itself like a cosmic sphere. The flat geometry of space, measured by satellites like Planck, suggests an infinite expanse, yet a looped universe remains possible, where every journey might return to its start. This question, unanswered, yet profound, reflects humanity's quest to understand our place, a quest driven by mathematics and curiosity. The idea that the universe might hold countless galaxies beyond our sight, or circle back in a gentle embrace, is like a soft melody, its notes blending into a harmony that invites calm reflection, a moment to rest in the mystery of existence. Let's linger on this scene, as if gazing at a cosmic map, its edges fading into the unknown. We ventured into the multiverse, where our universe might be one bubble among countless others, each born in a burst of eternal inflation. These bubbles, shimmering with their own stars and laws, could hold realities where gravity dances differently or atoms refuse to form. Scientists like Alan Guth and Andre Linde crafted this theory to explain the universe's uniformity, its smooth expanse shaped by a fleeting moment of rapid growth. The possibility that other universes exist, just beyond our reach, is like a quiet whisper, suggesting that our reality is one verse in an infinite poem, a thought that soothes with its boundless wonder, inviting you to dream of worlds unseen. Now, imagine a glowing bridge, its light stretching across the void, connecting distant realms. We explored wormholes, theoretical tunnels through space-time, born from Einstein's equations that might link our universe to another. These cosmic shortcuts, stabilized by exotic matter, remain elusive, yet they spark the imagination, hinting at pathways to other galaxies or even other realities. Scientists search for signs of warped space, using telescopes to detect gravitational lenses that might betray a wormhole's presence. The idea that the universe could be threaded with such passages is like a soft glow, illuminating the possibility of connection across the cosmos, a gentle note that resonates with the hope of discovery, easing you into a peaceful rest. Picture now a universe layered with hidden dimensions, folded into spaces smaller than an atom. String theory introduced us to these extra realms, where the vibrations of tiny strings shape particles and forces. These dimensions, curled into intricate Calabi-Yau manifolds, might determine why gravity is weak or why our universe supports life. Researchers at places like CERN probe for signs of these dimensions, seeking particles that vanish into unseen realms. The thought that our reality is a thin slice of a multi-dimensional cosmos is like a delicate thread, weaving a tapestry of wonder, a quiet reminder that the universe holds secrets beyond our grasp, yet ever present in its fabric. Let's pause here, as if floating in a cosmic sea, its waves carrying the rhythm of eternal cycles. The Big Bounce theory painted the universe as a phoenix, collapsing and rising anew in an endless dance. This cyclical view, rooted in loop quantum cosmology, avoids the singularity of the Big Bang, suggesting a universe that renews itself through quantum laws. Scientists like Paul Steinhardt explore this, searching for traces of past cycles in the cosmic microwave background. The idea that our universe might be one of many in a chain of rebirths is like a gentle tide, washing over you with the promise of continuity, a soothing vision of a cosmos that never truly ends. Now, shift your mind to a universe painted on a two-dimensional canvas, its depth and illusion crafted by information. The holographic principle proposed that our reality might be encoded on a boundary, like a cosmic hologram where every star and moment is a projection. Born from black hole studies by physicists like Leonard Susskind, this idea suggests that the universe's essence lies in its information, not its volume. Researchers seek clues in cosmic radiation, hoping to find patterns that match this holographic model. The thought that our three-dimensional world is a reflection of a deeper truth is like a soft light, glowing with the elegance of simplicity, a quiet invitation to ponder the nature of reality. Imagine now a cosmic mirror, reflecting our universe in a twin where time flows backward. The anti-universe theory suggested a reality of antimatter, balanced with ours across the Big Bang's symmetry. This mirror cosmos, explored through CPT symmetry, might hold the missing antimatter, explaining why our universe favors matter. Scientists search for signs in neutrino experiments, hoping to detect hints of this mirrored realm. The idea that our universe is half of a balanced pair is like a quiet song, its notes harmonizing in perfect symmetry, a soothing reminder that our reality might be part of a larger whole, connected across time's divide. Picture a sea of neutrinos, each one a whisper from the universe's first second, carrying secrets from before light could shine. The cosmic neutrino background, born in the Big Bang's earliest moments, offers a glimpse into a time when the cosmos was a fiery chaos. Scientists at experiments like Ptolemy aim to detect these elusive particles, hoping to uncover clues about the universe's birth and its mysteries, like dark matter or cosmic asymmetry. The thought that these ghostly messengers still drift through us, untouched by time, is like a gentle wave, carrying the promise of ancient truths, a quiet link to the cosmos's dawn that soothes with its timeless presence. As we rest in this cosmic reflection, let's weave these threads into a final tapestry, a vision of our place in the infinite. The universe, whether infinite or finite, a bubble among many, or a projection on a cosmic screen, is a story of wonder. Scientists have spent centuries chasing its secrets, from Galileo's telescope to the Planck satellite, each discovery a step deeper into the unknown. The edge of the universe, we've learned, is not a wall but a horizon, not a barrier but a question. Beyond it might lie more galaxies, other universes, or realms where physics bends in ways we can't imagine. The multiverse, with its countless bubbles, suggests a cosmos where every possibility plays out, a library of realities we'll never read but can dream of. Wormholes hint at connections, pathways through the fabric of space-time, while extra dimensions weave the rules of our reality in hidden folds. The Big Bounce offers a universe that breathes, reborn in cycles, and the holographic principle paints it as a projection, a delicate image of information. The anti-universe balances our own, and neutrinos whisper of a time before stars. Each idea, like a star in the night, shines with possibility, a gentle reminder that the universe is vast, yet we are part of its story. Now, imagine yourself as a traveler, having wandered through these cosmic mysteries, each one a light in the darkness. The universe doesn't demand answers tonight. It invites us to wonder, to ask what lies beyond, and to find peace in the questions. Scientists continue their quest, building telescopes, accelerators, and detectors, each tool a bridge to the unknown. The James Webb Space Telescope peers at galaxies born billions of years ago, while experiments like LIGO catch ripples in space-time, and others seek the faint hum of neutrinos. These efforts, like the stars themselves, are part of a grand human endeavor to understand our cosmic home. The thought that we're connected to this vastness, not as conquerors but as curious dreamers, is like a soft melody, its notes blending into a lullaby that carries you toward rest. Let's linger here, as if cradled by the cosmos, its mysteries wrapping around you like a warm blanket. The edge of the universe, whether a horizon of light, a boundary of information, or a gateway to other realities, is a reminder of how small we are, yet how profound our questions can be. The cosmos is a story without an end, a poem written in light, particles, and time. As you drift towards sleep, let these ideas become gentle dreams, visions of stars and bubbles, of cycles and mirrors, each one a piece of the infinite. If this journey has sparked your curiosity, leave a comment to share your thoughts. What do you imagine lies beyond the universe's edge? Your voice, like a star in the night, adds to this cosmic tale. For now, let the universe's mysteries guide you into a peaceful slumber, a quiet journey through the stars. Sleep well, and let the cosmos whisper its stories in your dreams, carrying you into a night filled with wonder.